Okay, so last time we were talking about vector line integrals. We got a nice little example here of a bit of good news to be on the lookout for. You'd be surprised how often this kind of thing happens. It's got certain things in common with symmetry. Y'all remember, I'm a big fan of symmetry theorems. It turns what could otherwise be a very hard problem into, well, ultimately a very easy problem. And what I'm going to call geometric good fortune will do the same thing in a different way. So here we go. We have a curve that's described by this right here, and you'll notice this does not give a full rectangular parametrization of the curve. But if you know rho, phi, and theta, then by simple formulas you can write down the rectangular parametrization. But it will be taking like sines and cosines and products, etc., of these expressions, and you can imagine that would be a pretty nasty looking parameterization. So yikes on the curve here that we have to deal with. And then we're looking at this vector field, and the question, of course, is to compute the vector line integral for this vector field on that curve. So how do we do that? So a couple observations to make. The very first observation I want to make is about this right here. Rho equals 1. That's for the entire curve. That means that we're always on this sphere. And if we're always on the sphere, then that means that our position differential, dx, is always parallel to the sphere. Right? If you can't move off of the sphere, then you're always moving along the sphere, aka parallel to the sphere. Okay, so that's the first observation. Next observation, let's look at the vector field. Notice that our vector field, also something really nice I can say about it geometrically, notice that it is a scalar multiple of the position vector. And the position vector, for a sphere centered at the origin, you gotta love spheres. The following property is unique to spheres centered at the origin. The position vector is always perpendicular to the surface. Right? Just geometric observation, right, from the picture. Gotta love spheres. So, alright, well what that means then is that altogether, these two, so that means that my vector field is perpendicular to the sphere. Yeah, so when we do this dot product, f dot dx, the things that we're dotting, one's parallel to the sphere, one's perpendicular to the sphere. That means that they are perpendicular to each other. That means this dot product is 0. That means this integral is 0, and we're done. Right? Didn't have to deal with that horrifying parameterization. Didn't have to, compute a nasty antiderivative. Just boop, 0. Gotta love it. So, how often does stuff like this happen? I mean, to be fair, this was a manufactured example. This didn't come naturally out of a real application. But honestly, this happens a pretty significant amount. Definitely enough that you want to be on the lookout for it. I was not taking data when I was an undergrad on how often this kind of thing came up, but just based on my memories. I mean, I think I feel pretty comfortable saying 10%. Right. So again, think about integrals that I did as an undergrad in the second major in physics. 20% were 0 by symmetry. Another 10% were 0 by various versions of sort of geometric good fortune. Right. Big deal. Very nice. So I hope y'all will keep a lookout for this sort of thing. Okay. Next sort of little small topic to note is kind of a notational thing. But a little bit of algebra that builds into it. Recall we have this formula for dx, old news. This traces back to early chapter 3, as I recall. Now let's look at the x prime itself, and we'll write that out in coordinates, which is ancient history, right? And we haven't exactly done that in this context before. I haven't written dx in terms of coordinates before, but we can, and now I'm going to. And then I'm furthermore going to distribute that dt. Unremarkable, right? Easy thing to do. And then I'm going to take a look at these individual coordinates. And for example, what can I say about scalar x prime dt? Calc 1, that's dx. That's literally just how much does the x-coordinate change. And then likewise, dy and dz. So what we have then is an alternative notation for our dx vector. Our position differential is a vector whose coordinates just represent the changes of the individual coordinates. Unsurprising as a result. Okay, so why are we talking about this? Well, if I just plug in this formula right here for my dx, and if I then let's just as a convention, why not? Let's use the standard notation for a vector field has coordinates p, q, and r. By the way, I don't really know where that convention comes from, but it's at a minimum, it's very common. I don't know if I'd go quite so far as say it's standard, but it's very common. And if I plug that in, now I have coordinates for the things that I'm taking a dot product of, and I can just crank out that dot product in the usual way, and what we find ourselves with is kind of a new alternative notation to represent vector line integrals. So there it is. It's kind of weird that we would do this, but you can, and this is just a different way to write vector line integrals. Now, should you write your vector line integrals this way? In most cases, I'm going to say no. If you look at these two options, this notation over here is clunkier. It's also what I would call less geometrically natural. You look at the original notation, F is a natural thing. It's a force or it's a velocity, right? It's something that's part of a physics problem. What is the dx? Well, it's displacement. Again, it's a very geometrically natural thing. It means something clear and natural in a question. By comparison, what is P? By itself. Well, it's the first coordinate of the vector field. Okay, yeah, but by itself, without making a reference to what we've already agreed, F is a very natural thing, but P on its own, not really. Right? Likewise, let's take dy. What is that? Okay, well, it's the second coordinate of the displacement vector. Yeah, but we've already agreed the dx vector is natural on its own, by itself. Why would I be interested in knowing along a piece of curve just how much y changes? Nothing else, no x, no z, just y itself. That's weird. Right? It's not clear why I'd be interested in that. So not only is this notation bulky, it's also relatively unnatural. So for Math 219, I don't really see any particular advantages to this. Right? And so my advice is in Math 219, unless there's some other reason to do so, I would encourage you not to use this notation. I don't think it's particularly advantageous. Which brings up the question, why am I wasting your time with it? And there are two good reasons for this. One is a cultural point. And independent of the fact that we're not actually going to do Chapter 8 in this course, in Chapter 8 there is some discussions. You can take a look if you're curious. You can just kind of flip through it if you just kind of want to see the flavor and the vibe of what it looks like. But in Chapter 8, they talk about this thing called differential forms. It is pretty sophisticated. It's pretty abstract. It's pretty mathy and proofy. Even more than the rest of the book is, which I've already mentioned, is kind of mathier and proofier than the course is intended to be. So that said, even though you're not responsible for it, I think it's good to know, just for cultural purposes, that differential forms really are very natural. Sophisticated, yeah, but ultimately very natural and arguably more to the point, very powerful. There's some big results in multivariable calculus that in order to prove them require the use of differential forms. They're just a really, really good idea, very natural, very powerful. It's good stuff. Now, again, all of those advantages are beyond this course. So I'm not expecting that you would use differential forms, aka I'm not expecting that you would use this notation anywhere in this course voluntarily, other than where they maybe the book might use this notation. But I want you to be aware, this is not just a bad notation we haven't gotten rid of yet. This is a wonderful notation, just that we don't have a use for in this course. Okay. Now that brings me to the second reason that I'm spending time on this, and that is that because of how natural and powerful differential forms are, a lot of people like this notation. And so outside of this course, in the real world, as it were, when you're taking engineering classes and physics classes, you're going to see this notation. It's going to come up. And when it does, you need to know what it means and what to do with it. So I feel it necessary to show it to you, just if only, so that you can deal with it when it comes at you at some point in the future. And just to be clear, what should you do with this notation when you see it? Well, these things, the P, Q, and R, don't forget, that's just a fancy way of telling you what your vector field is. So interpret from the P, Q, and R what your F is. Likewise, don't forget that the dx, the dy, and the dz, that's just kind of an alternative way to represent the x vector. In other words, that's just a recognition of the fact that we are doing a vector line integral of that vector field. So with that in mind, whenever you see this, you can just immediately rewrite it, or at least rethink of it like this. So that'd be my advice on how to treat that notation. Okay, how we doing? Is everybody with me? Okay. All right. Okay. Symmetry theorems. Again, big fan, right? I've made no secret of that. I'm going to show you another one for scalar line integrals. There is another symmetry theorem. You'll notice from the layout on the page, it looks just like our previous symmetry theorems for double integrals, for triple integrals, right? Morally, this is the same thing. It's just like with those previous theorems. If your integrand is odd, if your domain is symmetric, your integral is 0. You're done, right? Wonderful theorem. Very powerful, very convenient. Big fan. Notice, though, you do need for both conditions to apply, just like our previous theorems. And you do need for both to use the same line, just like in our previous theorems. Right? So same warning, same uses, same everything, really. Right? So very, very convenient and very familiar. How we doing? You okay with that? So be on the lookout for that. Very useful. Asterisk. This is only for scalar line integrals. Importantly, only for scalar line integrals. It does not work for vector line integrals. And furthermore, there just is no what I'll call odd symmetry theorem. It does not work for vector line integrals. So beware, right? You got to be careful when you're looking at integrals and wanting to use symmetry. This is just another landmine. You can think of it that way. Make sure that you're not trying to use an odd symmetry argument on vector line integrals. There is no such theorem or argument. It just doesn't work. I can give you a quick argument as to why it doesn't work. If we're reflecting over that line, for example, and let's suppose that our domain is a curve like this, which I am attempting, I do better than that. I'm attempting to draw there a curve that is symmetric over that line, right? Well, you can chop it up into little pieces, and we can look, for example, at this little piece there versus this little piece there, and hey, check it out, the DS's are the same, and that's nice. So it's tempting to look at this and think, okay, well, looks like we have a match. But very importantly, keeping in mind that we're looking at a vector line integral here, you've got to think also about your dx, aka TDS. So ds by itself is not enough to look at, we also have to understand the t. And if you look at the t here, the t vector for this first piece is like that. The t vector for the second piece is like that. They are not the same. These aren't, right? You can see perfectly clear in the picture, they're not the same. They're also not negatives of each other, so you can't sort of tweak this and say, oh, we'll use even instead of odd or something like that. They're just different. So, again, make sure, do not try to apply symmetry to vector line integrals. Everybody with me? Dangerous, possible, easy oops to make there. Okay. All right, moving along. So we're into section 6.2 now. This is our entry into my favorite part of the course. The reason that multivariable calculus is my favorite course to teach is these various big theorems that we're going to see in chapters 6 and 7, and this is really the first one of them. There's a lot of ideas that come up in discussion of Green's theorem and the divergence theorem and the curl theorem that we're going to be getting to later. There's a lot of concepts. The concepts are a little bit abstract, a little bit weird. A lot of this is going to seem strange. Get used to it. That's the nature of the ideas that we're going to be doing here. So be on the lookout and give yourself plenty of time, if I can advise you accordingly. Give yourself plenty of time to digest this. Don't expect that this is something that you're just going to immediately understand and get comfortable with immediately right here in class. Of course, I always advise, but especially here I advise that you re-listen to key parts, things that you found confusing in lectures, especially this lecture and the related coming lectures. Re-listen to portions that you found confusing. Chew on it a little bit. Ask questions. My office hours, other instructor office hours, etc., etc. Come back, listen to it again. Give yourself multiple passes through, different forms of back and forth, so that you can really comfortably digest all of this stuff. Okay. And the punchline is going to be, we're going to have some extremely powerful theorems, and the way that they fit together is really remarkably, I think these are beautiful ideas myself, but also ultimately very simple in how they all fit together. So that's a lot of preview, but that's what to be on the lookout for. Okay, so there's various tools that we're going to need to develop, eventually building up to Green's theorem, that we may or may not quite get to by the end of today. We'll see. But various tools that are going to kind of fit together at the end. For the moment, I'm going to talk about these tools independently. You'll kind of see how they fit together as we go. But the way they fit together, again, it's really going to reveal itself at the end. So tool number 1, I need to develop the idea of a boundary. Not really that new of an idea, if you think about it. If you have some region, like I've got some region here in gray, that region D. Boundary means, well, you look at it's the dividing line between D and not D, right? It's where's the fence that keeps D inside. Think of it in different ways. So, boundary of a two-dimensional region we think of as being a curve. That's actually not quite good enough. We're going to need to refine this idea. I need to build up a little bit more. I need for my boundary to be more than just a curve. I need it to be an oriented curve. And the reason I need it to be an oriented curve, we will eventually be doing vector line integrals on it. And I'm going to remind you, when you do a vector line integral, let's see, we probably have this back here somewhere. Where it's pretty far back here. Wow, here we go. When you're doing a vector line integral, right? I need my domain to be an oriented curve. That orientation taking the form of an indication, by whatever way, an indication of not just what curve am I moving along, but which direction am I moving along that curve? Right? So this is what we mean when we say the domain of a vector line integral. It's got to be oriented. If I just say that, too far. If I just say that boundary is just the curve, that's, kind of where the domain ends. There is no implicit orientation. So we need to make a choice. We need to have an implicit convention when we say the word boundary. What orientation is to be understood there? And there is an answer. I'm going to confess in advance, this is an arbitrary choice. But it's also a very standard arbitrary choice and has been for well over 100 years, 150 years, I'm not exactly sure, but a long time. And so think of this arbitrary convention as kind of like in physics. If you think about it, electrons are negatively charged, protons are positively charged. Y'all may remember that from physics. Why? There's nothing intrinsically negative about electrons. Electrons and protons are opposite charges, but there's nothing magical that means one of them has to be the negative one. So why did they call electrons negative and protons positive? It was arbitrary. But it is standard, and everybody's got to get on board. And if you decide to create your own physics where electrons are positive, it's unthinkable, unthinkably confusing, right? So in the same way, this is standard, and we have to stick with it. Here's the convention. When you are going in the correct direction, if you are going in the proper orientation along the boundary curve, as you go in that direction, the region whose boundary you are moving along must be on your left as you move in that direction. Now I appeal to your sense of geometry. If, here's this boundary curve I've got moving along the bottom here. If I'm going in the direction of this green arrow, imagine me walking along here. The region's on my left. Right? And on the other hand, let's imagine I was going the other way. Let's imagine that I was going this way. If I was going that way, the region would be on my right, which is different. Right? So, whichever direction it is, in this case it's that direction, whichever direction it is that puts the region on your left, that's the correct orientation. That's what we mean when we say the orientation of the boundary. How are we doing? Yes? This is just what we mean by an orientation is just an indication of which direction you're going, right? And when you're talking about which direction you're going along a curve, let me clean up the thing here. If I am at this point, pencil. If I'm at this point, the two directions along the curve I can go are that way and this way. And so it doesn't really matter what your perspective is, right? It's not as seen from anywhere. It's just those are my two options. And if I'm going this way, the region's on my left. So that's the correct direction. Does that make sense?
And the region, is the gray thing, the big gray blob?
Yeah, that's right. The big gray blob is our region D. That's right. Yep. Let's see another example. Here again, big gray blob is our region. That's D. That's the thing whose boundary I want to talk about. The boundary, of course, is this curve. I'm only drawing just a portion of it. I don't want to get distracted by the whole rest of the shape here. But that's a portion of the boundary. And which direction do I need to walk along this curve such that this, namely into the region D, into the region whose boundary I'm talking about, which direction do I walk to make that on my left? And the answer is I would need to go this way. Because you could just imagine yourself, if you're walking along this way, the region's on your left. You might see that. Okay, arbitrary convention, highly standard, very important that we're all on the same, arbitrary page, and so this is what it is. Now, there is an alternative version of this. Very popular. A lot of people like to think about it this way. It's also a little bit wrong. So beware of this, but you will see this point of view presented. It's like the following. So if this is your region, for example, which direction do I move along the boundary to make the region on my left? And what you notice pretty quickly is that the direction that you have to walk is always counterclockwise around this boundary. And you can draw other pictures that are kind of, along these lines. Let's be deliberately sloppy about this. And in some sense, kind of for lots of different shapes, almost any shape you can think of, you will find that moving such that the region's on your left has you going around counterclockwise. Except, it doesn't always work. Here's the counterexample, or a counterexample. Let's suppose that this is your two-dimensional region. And that's your two-dimensional region. Notice if I go this way, the region's on my left. Counterclockwise. It's looking good so far. What's the problem? The problem is, if I look on this part of the boundary, that's the direction I have to go to keep the region on my left. And it's clockwise. Right? So it's just not always true to say counterclockwise. And, you can make the observation, if you'd like, that this counterclockwise rule does always work on the outside portion of the boundary. Sure. But once you get to the point where you're talking about, well, it's this in this case, but it's something different in a different case, I think the seeming appeal of simplicity is gone. In order to make sure that you're correct, you have to make this really a less desirable point of view than I think this up here is. So just always move such that the region's on your left. I think that's the best. It's the uniquely reliable way of thinking about it. Okay. All right. So that's our first concept. Next concept. Kind of an old idea. We've actually done a lot of this throughout the course. I just didn't use the word. The word here I want to introduce is the idea of accumulation and an accumulating quantity. Here's the idea of accumulation. What we mean is the whole is the sum of the parts. Chop it up, add it up. I've said that a million times in regards to integrals. Every time we do an integral, we're taking a whole, we're chopping it up into pieces, and we're computing the quantity in question on the whole as the sum of the quantity in question on the parts, added up over all the parts. So anything that has this property, for example, mass, anything that has this property, we say accumulates over the area. So, for example, the mass in this whole thing there, that orange mass, that is the sum of the mass on the left piece plus the mass on the right piece. Right? The orange mass is equal to the purple mass plus the blue mass. The whole is the sum of the parts, right? So it's tempting to say, well, how could this not be? I mean, this applies to, golly, everything we've talked about in this course so far. Mass, the whole is the sum of the parts. Population, the whole is the sum of the parts. Work that it takes to accomplish a task, blah, 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 we can think of as the whole is the sum of the parts. So, really, I'm just giving a name, namely accumulation, to something that we've used a million times. And before I get to a counterexample, let me complete the discussion of lingo. Quantities that have this property, you can say they accumulate over the area, or sometimes grammatically, linguistically, it's more convenient to say it's an accumulating quantity. It's understood that what we mean is it's accumulating over the area. by which I mean, when I say over the area, that means that it is the area that I'm chopping into pieces. Okay. All right. So, why give a name to something that we've never seen not apply? So, let me show you one where it doesn't apply. This is a perfectly reasonable concept, and accumulation does not work. And let's talk about perimeter. Perimeter does not accumulate over areas. Let me show you why. We think about the whole. Here's the whole. Let me geometrically here draw a picture of the perimeter. Here's the perimeter. Perimeter is that distance right there that I have in purple. Again, keep in mind, I want to think of perimeter as something I associate to the area. I know that seems weird. You might want to think of perimeter as something that we associate to the boundary curve. Very importantly, though, the boundary curve is not what I'm about to chop in half. Right? I am in particular going to be chopping the area in half. And so I have to think of the perimeter as something that's associated to the area. Okay, so that said, there's the perimeter of the whole. Now let's look at, let's see, and let me do it like this. Thinking about perimeter. Let's look at the left side. There's the left side. Let me draw a picture of the perimeter of the left side. The perimeter is this distance, kind of going along like this, followed by that. So what I have in green there is the perimeter of the left half of the area. Now I'm going to look at the right half of the area. Let me draw a picture of the perimeter of the right half of the area. Like this. And so now we can just look at this picture and ask, is the purple distance equal to the green distance plus the blue distance? And clearly not. Right? In fact, I can visually demonstrate how it fails by kind of pairing up. Notice that as I go along here, the purple and the green areas, the purple and the green lengths are exactly the same along this orange here, and then here it's the blue and the purple that are exactly the same. So all of that just cancels. Let me just kind of erase. I know that those terms cancel in the equation. They're the same on both sides. Is there zero left over? No. Tragically, there's a bunch of curve. There's a bunch of distance left over. So in this case, the whole is less than the sum of the parts. So perimeter is not an accumulating quantity because there's leftover that's not zero. Yeah? Can we see what I mean? So it's worthwhile to talk about this idea of an accumulating quantity because it does not always apply. There are easy examples. Perimeter, I think, is a nice, easy one to get started with. Easy examples of quantities that you can associate to areas that don't accumulate. The whole is not the sum of the parts. You cannot compute this perimeter by, doing a double integral by chopping up the area into a bunch of little pieces, and no, that just does not work. Okay. All right. Okay. Now, let's try to put our finger on, in some sense, why did this not work? We don't have to get precise about this. It's tempting, though, to kind of oversimplify and say, well, look, mass is a physical, concrete thing, and the rules of our physical universe are that you just can't create or destroy mass by making arbitrary distinctions about where I draw lines. Mass is what it is, right? And so, in some sense, the physical reality of the universe is why mass is an accumulating quantity, right? Whereas perimeter, not so much, right? Perimeter, it's not really a concrete stuff. right? It's a geometric concept that we made up. And so you can imagine that, we can make up all sorts of non-concrete, non-physical nonsense that might have all sorts of failures of properties, because the physical universe just has no interest in the matter. That's a point of view. But it is not that simple. There are geometric constructions that we can make, mathematical objects we can create that do accumulate, that do behave kind of like mass does. They behave like a stuff in the sense that the whole is the sum of the parts. They behave as if they are physical quantities, even though they aren't, even though they're purely mathematical constructions. And the one in particular that we're going to talk about now, boundary circulation. Right? Recall circulation. Circulation means vector line integral around a closed curve. Boundary circulation, specifically, this is just kind of a verbal reminder that specifically we're thinking of this as on a curve that is literally a boundary of a region, and furthermore, this is kind of a reminder that we are thinking of boundary circulation as something that we associate to the area that you're going around the boundary of. So I claim that boundary circulation accumulates unexpectedly. Let me try to persuade you this is true. So we're going to play the same game we have before. Let's see here. Let's look at the whole region here. There's a whole region. The boundary circulation is a line integral that you compute around that boundary curve, but wait, no, it's more complicated than that. Boundary circulation, this keyword boundary, remember, first thing we talked about today, when you hear the word boundary, that means there's an orientation. There's a specific orientation following a specific convention. And to add in that orientation here, boundary goes that way. Like that. So this along that oriented curve is how you would compute boundary circulation for the whole there. Is everybody with me so far? All right, now let's do the pieces. We'll look at the left piece. Let's talk about boundary circulation on that left piece. Well, the boundary is kind of like this, but there's another chunk like that. So that's going around the boundary of the left half. Orientation, as per the convention, regions on my left. So there's the boundary circulation on the left half. Now we'll do the right half. There's the right half going in the appropriate direction. We're going like that and then down like this. That's boundary circulation on the right half. Again, you look at the, purple versus green plus blue. Let's compare the whole and the sum of the parts. All of this orange here, green is canceling with purple. Over here, blue is canceling with purple. In some sense, a bunch of stuff cancels. And what's left over is this right here. Now, it's tempting to say, just like with the perimeter counterexample, that, check it out, there's stuff left over. If there's stuff left over, that means there's a difference between the whole and the sum of the parts. This is the difference right here. How can they be the same if there's a difference that I'm looking at right now? Right? And here's the twist at the end. These two pieces of line integral are over the same edge, but with opposite orientations, which means their values are negatives of each other. That means that they cancel. And in fact, that difference that we think we're looking at there, that difference is actually zero. So they're the same. The whole is the sum of the parts. And it's all because of the orientations. It's ultimately all because these orientations are opposites of each other, which geometrically is a consequence of our rule about how we defined orientations, which, again, was arbitrary, but it was arbitrary in a very clever, critical way that makes these opposites of each other. Okay. Is everybody on board? Is that a no? Okay, all right. Anybody else? Okay. Okay, so we have an accumulating quantity. Furthermore, now you might complain about what I've done here and say, well, yeah, that explains what happens if you chop it in half. What if you chop it into a bunch of pieces, like we do when we do integrals? Well, let's look at this picture. All right, here I've got a region that I've chopped up into a whole bunch of little pieces, and let's kind of take them one at a time. Let's look at this piece right here. That piece, the boundary circulation is computed as these 4 line integrals on those 4 edges, oriented as shown. The regions on my left as I go around, right? Loosely speaking, counterclockwise. Ditto for this region. Now this is a slightly weirder shaped region, so there's kind of a 5th little edge over there. But no worries. And then this region here, counterclockwise, blah, blah, and etc. And you can do this, draw all these arrows together, looking at the counterclockwise oriented boundary circulations on all of these individual little pieces, and notice the cancellation happens in morally the same way on all of the shared edges. So this edge right here, for example, I'm going up on the green side, I'm going down on the blue side, cancel. Ditto there, cancel. Ditto there, cancel. Cancel, 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 cancel. There's a lot of, this is kind of fun actually. You get to go through and cancel all of these shared edges. They all cancel because on each of these shared edges that I've highlighted in red, there's a left side and there's a right side. You go in opposite directions on those 2 sides, which therefore give you negative values of each other, which therefore cancel. And what's left? Once I've added up all of these, sum of the parts, boundary circulations on each one of these parts, the pieces that are left over are the pieces where there is nothing on the other side to cancel with. And namely, notice what that means is you have boundary circulation around the whole. The boundary around the entire unified thing. Yeah.
So if you have like a curved edge, right, and then like you're saying like the big circulation can be calculated by the smaller circulation, right?
The sum of all the smaller ones, yeah.
But if you're trying to use like an integral to calculate that with like smaller squares,
yeah,
then how do you do like the curve? Because at the curve, won't there always be a corner there rather than a straight horizontal line?
I'm not following. What do you mean?
Like right now you have squares, but then when it reaches the edge, that's not like a square.
You're worried about this piece right here not being a straight line?
Yeah.
All right. So keep in mind the definition of the quantity in question is just its boundary circulation. Oh, I need to zoom out. Which is just a vector line integral, and boundary circulation is defined on any curve, right? So, for example, you can talk about the vector line integral on that curve. Now, that one happened to cancel, but whatever. Go ahead.
Sorry, isn't the whole point of having like smaller squares so that it's easy to calculate circulation on a square rather than the entire?
Well, where we're going with this, we'll get to. Okay. So you're kind of looking a little bit too far ahead, but and I may have just misunderstood your question, but whether or not what we're canceling on is or is not a straight line just doesn't matter. Boundary circulation is just defined as a vector line integral on the curve, the understanding that the curve is a boundary of something, and vector line integrals are perfectly well defined, independent of whether the curve is straight. I'm not sure if that.
Go further.
Yeah. See if I don't inadvertently answer your question over the rest of class period. Yeah. Okay. So all right. So now here comes a kind of a weird idea. This is a repetition of something I said before, but I want to explain why this is so important. So what I said before, and why don't I scroll back to where I said it? You want to think of accumulating quantities as something we associate to the area. Right? So mass accumulates over the area because it is the area that I'm going to chop up into pieces. Right? And so when I ask the question about, for example, is perimeter a quantity that accumulates over the area, it's because I'm going to chop up the area into pieces. I am not chopping up the boundary curve into pieces. That's just not what the argument is about. That's not what we're doing. Right? So anytime you have an accumulating quantity, you associate it to the area. Now, let me talk about that in this context here. I've claimed that there's a relationship between boundary circulation on the whole and boundary circulation on the parts. The first thing I'm going to do is ask a question that makes seemingly no sense the way I'm about to phrase it, because I'm going to phrase it wrong. Right? I'm going to think about it in terms of curves, and you're just going to see how wrong this is. So let's suppose I'm interested in this boundary circulation here. And I'm going to ask seemingly a ridiculous question. How much of that boundary circulation happens as that boundary circulation? And this seems a ridiculous question. Well, the green boundary circulation is computed on this green curve. The orange boundary circulation is computed on the orange curve. They're different curves. I don't even know what you mean, how much of this happens there. They're completely unrelated things. This question seems wrong because we're thinking of boundary circulation the wrong way. Again, we want to think of accumulating quantities as associated to the area. Now I'm going to rephrase the question. Properly thinking of the boundary circulation as something associated to the area. And it looks like this. How much of the boundary circulation on this green region comes from the boundary circulation on this blue region? Sure, that's a perfectly reasonable question. Just like any other accumulating quantity, let's talk about it in terms of mass. How much of the mass in the green region is in the blue region? Natural, easy, perfectly reasonable question, because the blue region is part of the green region. It's a subset of the green region, right? It's one of the pieces that, between it and several others, makes up the whole green region, right? So, just like with mass, that I think of as something that's associated to the area, that I think of as distributed over the area, I want to insist that we think of boundary circulation as something that we associate to the area, right? And that we think of, even though it kind of isn't, right? We want to think of it as being something that is computed for the area. Now, in practice, day in and day out, when you literally compute a boundary circulation, yeah, you go along the perimeter. Of course you do, right? But that's not the way I want to think about it. The point being, it behaves, because it's an accumulating quantity, boundary circulation, it behaves just like mass does. It accumulates just like mass does. So I want to think of it as distributing across the area, like a kind of a physical stuff, just like mass does. And again, I guess you could say you don't have to think about it this way, but some valuable properties of boundary circulation are consequences of the fact that it behaves like this, and so it's valuable to think of it like this. Even if that seems weird, still valuable to think of it that way. Okay, so and we're kind of out of time here, aren't we? Now, shoot. All right, you know what? This is a pretty good place to draw the line. We're going to draw the line right there, and we will pick up here on Friday. We are so close to being able to state a shocking theorem called Green's theorem, and so think of this as a cliffhanger, end of season cliffhanger, and we're going to have the shocking conclusion on Friday. See y'all on Friday. Have a good one.